Hey there, calculus fans. I'm going to do a video, the third part of my series on integrals that are my favorites. You know, really after the first two, I was kind of stuck. I will, as I think of things, I'll be adding to my various video series I'm trying to make. But as I was doing something else, I was reminded of this integral, which comes from the study of bell curves. Now that's this integral from negative infinity to infinity. It turns out this has a nice closed form answer in terms of well-known constants. Now, a small comment is if you're someone that just took calculus, maybe with me, you know that this integral is really hard to deal with. You can try substitution, whatever. You know that if you inserted an x, it would be doable, but without the x, it's not. If you take Math 126, you're going to learn that you can replace this with its Taylor series, and that's kind of the best you can do. It goes negative x squared plus 1 over 2 factorial x to the fourth, negative 1 over 4 factorial x to the sixth, plus 1 over 6 factorial. So that's something you will do in Math 126. You'll learn how to turn essentially anything to a polynomial, and an advantage is that you can integrate. Yes, the answer is an infinite series, but that's often the best you can do. And it's a pretty darn good answer. And this is an important function because it comes up in the study of bell curves. This function, if you were to graph it, is this shape. So if you take probability, you'll study that a lot. So this integral is important because you would like it to be. It turns out it's not 1. It's not 100%. You have to rescale the function in order to get that correct value. Okay, so what do people do? It turns out this ends up being the square root of pi, which is remarkable. And I'm going to call that a for a second. And the typical proof goes like this. It says, I'm going to do the following. I'm going to rewrite the exact same thing. And I'm going to multiply it times itself again. If we can figure out what that is, that's a squared. It turns out that's going to be pi. Now, how in the world is that helpful? You've just written the same thing twice with a different variable. Well, it turns out you can write this as what we call an iterated integral and put these two things together. Now, the precise details of that you'll cover in chapter 15 of Math 126. And there's two things about this. This represents a surface, something that's above the ground. I always just draw the same flying carpet, even though this actually is going to look like a bell curve in 3D. And then they give you a region on the ground, and your goal with double integrals is to find the volume between the region on the ground and the surface. Now in this case, the region on the ground is everything. It's the entire xy plane. And the question is asking, what do you get in the limit? Basically, if this just gets bigger and bigger and this gets bigger and bigger, what does this approach? It turns out it does approach something. But there's a better way to handle that, which is to think in terms of circles. That's the polar coordinate approach. And there's some nice things about circles. If you have a point on the edge of a circle, and if you know the radius, there are several things you can say. You can say x is our cosine, you can say y is our sine, you can say x squared plus y squared is r squared, and this is all stuff you'll study in section 15.3 in Math 126. You'll have to review some polar to get that. Okay, so instead of thinking of it this way, we're going to think about what happens as we go further and further out. It turns out that's okay, and there's a lot of theory about why that's okay, why that'll give us something equivalent, but I'm not going to do that here. I'm just going to move forward. Okay, so if you're trying to describe this in polar, we think in terms of angle. Now the angle goes from 0 to 2 pi. It doesn't go to infinity. And then we describe it in terms of r. Now, if I give you a certain number, like a radius of 3, we would say r goes from 0 to 3. And that will get you everywhere. It mows the lawn in an unusual way. And you'll talk about that in Math 126. But we really want to know what happens as this goes to infinity. It turns out that's okay. You can do this. Integral from 0 to 2 pi. Integral from 0 to infinity. You replace x squared plus y squared with r squared. And then there's one other piece of the puzzle. And that's something you'll talk about when you talk about polar coordinates. It turns out what this represents is the area of one subdivision on the ground. Now, if you're working in polar, the subdivisions look a little different. There's an adjustment you have to make for that. This represents the change in r. This represents the change in theta. And it turns out the change in theta is not a length. If you want the length, it's the arc length around the edge of your circle. And then you always can get that by taking whatever angle you have and multiplying times r. So what we say is that the area, the change in area here is delta x times delta y, but in polar the change in area is r times delta r times delta theta. Now there's a lot of subtleties to talk about, but that r is basically coming from the fact that if you have an angle and you want a length, you have to multiply times r. What I tell students is you talk like a pirate. This becomes r d theta. And that's what made me think of this, because I was thinking about something else I do in math where I talk like a pirate. And then I'm going to finish this up fairly quickly. That's the key piece. It turns out since there are no other thetas in the problem, you can integrate that very quickly. Again, I'm not showing all the details. And then we're going to write this as a limit. The limit as t goes to infinity. The integral from 0 to t. And then the rest of this I'm going to do with the substitution. So if I call that u, then the r cancels, and we can do substitution. You end up getting e to the negative u, and you get 1/2 du. You do have to change this to t squared. So I'm skipping some steps. I actually already did this video, and then I realized some of the visuals did not get brought over. So the second go around, I'm doing it faster, which is probably better for everybody anyways. The integral of this is this, from 0 to t squared. Let's plug this in. So we get pi times the limit, when t goes to infinity, of negative e to the negative t squared, minus negative e to the 0. Now you should already know that that approaches 0 as you go to infinity, but if you don't, I tell students, rewrite negative exponents as fractions if you're trying to figure out what happens in the limit as you go to infinity. So you should see that goes to 0 and you get pi. And there's our result. This is pi, which means this is square root of pi. And that comes up in all formulas. So this always has to be explained in a probability class because it comes up in the formulas for the bell curve. When you start to include the mean and the standard deviation, there's always this 1 over the square root of pi. In fact, it's usually 1 over the square root of 2 pi. The 2 is coming from the fact that the integral usually has a 1/2 in it to try to scale it in a certain way. But anyways, this is an essential part of probability in the bell curve, is knowing the value of that integral. So I would say this is one of my favorite integrals, and it's just cool how we use polar coordinates in this very unusual way to ultimately take something where we couldn't use substitution and turn it into something where we could. All right, hope you find that interesting.